Some limits produce indeterminate forms. Recall that 0 divided by any non-zero number causes a zero quotient. Any non-zero number attempted divided by 0 is undefined. And 0 over 0, 0 divided by 0, it's indeterminate. We don't know what it's equal to. So if we have a limit that produces an indeterminate form, we have to do some further investigation. On the screen, you see two graphs that are practically identical except for at 1, 2. The graph on the left has a missing point. It's not defined at 1, 2. The graph on the right is defined at 1, 2. These functions are equal everywhere except for at x equals 1, which is perfect because we can use the function which is defined to find the value of the limit for the function that is not defined. Let me show you how it works. If we had started with x squared minus 1 divided by x minus 1, and we wanted to find the limit as x approaches 1, we know that direct substitution causes an indeterminate form. But we can find this twin function, which is defined, simply by factoring and reducing the common factors. Notice that the result is x plus 1. That's the function which is defined at the point 1. Let's walk through this. Looking at the limit of the function x squared minus 1 divided by x minus 1, when we allow x to approach 1, causes an indeterminate form. Direct substitution gives us 0 over 0, so we can't use direct substitution here. So we're going to try to simplify and find this twin function, which is defined at the point we're interested in and is equal to our function everywhere else. So we factor our numerator using a difference of squares, and then we reduce the common factor x minus 1 to see the twin function, x plus 1. So these two functions are equal to each other everywhere except at the one location where x equals 1. So we will evaluate the limit that we started with using this twin function, and now we will be able to use direct substitution where we just replace the x with 1 and simplify. So the limit of the function we started with, we couldn't use direct substitution, but once we found this equal function, the twin function, we were able to find the limit by using direct substitution there. So we found the limit was equal to 2. Let's try another one. Here we have x squared minus 3x, all divided by 2x squared minus 5x minus 3. And we're looking at the limit when x is approaching 3. We try direct substitution and we get 0 over 0. Plugging 3 into all of those x's causes a 0 in the numerator as well as a 0 in the denominator. So we're going to try to simplify algebraically, just like the last example. I can factor out a common factor in my numerator of x, but then in my denominator I have a trinomial. To factor that trinomial, I'm going to use the AC method. So I'll multiply the coefficient on x squared times the constant term, find all of the factors of the constant term, and then, sorry, not all of the factors of the constant term, but all of the factors of this product, a times the constant term. So I factor out -6 to find every possible combination of two numbers that multiply together to give me -6. Then I pick the two numbers that would add together to match my center term, this linear term in my trinomial. -5x is the exact same thing as -6x plus positive x. So I make that replacement, and now I have a 4-term polynomial rather than a 3-term polynomial. This allows me to group two terms together and factor out the common factor from each of the two sets of terms. Notice that after pulling out the greatest common factor of those two groups, I created another common factor. They both have x minus 3, so we factor out the x minus 3 and copy down what's left. So we factored our polynomial in the denominator, we bring it back up to our rational function, and look to see if we have any common factors. We certainly do. X minus 3 can be divided off, leaving us with x divided by 2x plus 1. We have just determined that we have a twin function. Our original function is equal to x divided by 2x plus 1 everywhere except for when x is equal to 3. So we won't let x equal 3. But what's great about limits is that we're allowing x to approach 3, meaning x can be any number you can imagine, but it can't be 3 because it's going towards 3. You can't be 3 and go towards 3. You'd have to be a number other than 3 and then head in the direction of 3. Evaluating our limit using x divided by 2x plus 1, we can use direct substitution because we don't get a 0 in the denominator. Replacing our x's with 3's and simplifying, we find 3/7. So the limit of the function x squared minus 3x divided by 2x squared minus 5x minus 3 when x is heading to 3 is 3/7. We couldn't use direct substitution initially because it caused indeterminate form, but we simplified algebraically to find a twin function, and then we used that twin function with direct substitution to find the value of the limit. Not always will algebraically simplifying a function fix the problem. This function, the square root of x plus 2 minus 1, divided by x plus 1, has another indeterminate form, just like the other examples. So if we allow x to approach -1, we do get 0 over 0. Direct substitution puts us right up against a wall. To fix this, we're going to multiply by using the conjugate. What is a conjugate? A conjugate is the same two terms, but with the opposite sign between them. So the square root of a with b, those are the two terms, and if it was a plus, then the conjugate would be a minus, and if it were the opposite, a minus, then the conjugate would be a plus. So you copy the terms, but you change the sign between them. We're going to use the conjugate on our function to get rid of the radical in the numerator. I'll take the conjugate of the numerator and multiply it to the top and to the bottom of our function. This is going to create a difference of squares in the numerator. So we can take our first term, which is the square root of x plus 2, and then we can square it and subtract our second term, which is 1, and square it. This is where we're creating a difference of two things that are being squared. And if we simplify, the square root being squared goes away, and 1 squared is just 1. So our function reduces to x plus 1 all divided by x plus 1 times our conjugate. Notice I'm not multiplying out my conjugate. There's a reason for that. My numerator matches one of the factors in my denominator, and I want to reduce that so that I can eliminate that 0 over 0 indeterminate form for x equals -1. Dividing that off, I'm left with 1 over my conjugate. So the original function is equal to 1 over that conjugate as long as x is not equal to -1. And for evaluating limits, this is going to be just fine. We now evaluate our limit using this twin function and direct substitution. Replacing our x with -1 and simplifying, we get 1/2. So the limit of this complicated function we were able to find is 1/2. We checked direct substitution and we found an indeterminate form, so we used the conjugate to find a twin function that we could use to evaluate our limit. We've seen functions with indeterminate forms that we can simplify algebraically, and we've also seen functions of indeterminate forms that require use of the conjugate. But this function isn't quite either of those. Here we're looking at a complex fraction. That means we have fractions inside of fractions. Our numerator is two fractions. In this case, our limit produces an indeterminate form just like the other two functions that we just looked at. However, we're not going to use factoring or conjugates to fix this indeterminate form. We're just going to simplify the function. The best way to do this is to find the least common denominator out of all of the terms in my rational function. Really, I just have two denominators. That's the x plus 1 and the 2 that appear in the numerator. My LCD is going to be the combination of those two factors. I'm going to multiply the LCD to my entire numerator and to my entire denominator. We can distribute that LCD into the two terms of the numerator, and it's going to reduce the fractions that are appearing in my numerator. Let's walk through it. In this case, the LCD is x plus 1 times 2. It's just the product of the two denominators that we see appearing in this complex fraction. So if we use that as our LCD and multiply it to each term in the numerator as well as the entire denominator, we can see that we'll be able to reduce the denominators in our numerators, leaving us with just a 2 minus x plus 1. It's very important to have parentheses around that x plus 1 because we're subtracting that entire quantity. So it's not just minus x, it's minus the x and the 1. And then in the denominator, I'm leaving everything factored because I'm hoping that I'm going to be able to reduce that indeterminate form factor that's hiding in our function. So don't multiply out the denominator. We can simplify our numerator by distributing that minus and combining like terms. We have 1 minus x divided by x minus 1 times x plus 1 times 2. Now here we don't exactly have a common factor in the numerator and the denominator, but we can force that to happen. Up top we have 1 minus x. On bottom we have x minus 1. Those are the same terms, but with opposite signs. On top, the x is negative. On bottom, the x is positive. We can fix this by multiplying my numerator by negative 1 squared. Negative 1 times negative 1 is positive 1, so I'm not actually changing the value of the function. But if I separate that negative 1 squared to where one of the negatives is multiplied into the 1 minus x, it changes the sign of the terms. The other negative just hangs on for the ride. So I have now x minus 1 times negative 1 in my numerator. And when I rewrite the function like this, I do have a common factor that I'm able to reduce, leaving us with the twin function, negative 1 divided by 2 times x plus 1. That is exactly equal to our original function everywhere, except for when x is equal to 1, since we divided off that factor. We'll use that to evaluate our limit with direct substitution, replacing x with 1 and simplifying. We get a limit is equal to 1/4. So here we did find an indeterminate form that we fixed by using the LCD to simplify our complex fraction, and then we were able to do direct substitution on that twin function to evaluate our limit. Not all limits can be used with these limit laws. For example, the function you see on the screen violates the initial conditions for our limit laws. You cannot have a 0 in the denominator and still apply your limit laws. Remember that rational function theorem? When we're trying to evaluate the limit of a rational function, the denominator cannot be equal to 0 with direct substitution. Well, that's exactly what's happening with the two terms that we see here. I can't just separate the terms, apply the limit to each one, and then use that rational function theorem. Instead, what we need to do is fix the problem that we have. So we can't apply the sum limit law because the two terms on their own don't have limits that will exist. So instead, we'll manipulate algebraically. We'll take our function, find a common denominator, and simplify. Now we have x divided by x times x minus 5. We can reduce the factors of x on top and bottom, leaving us with 1 over x minus 5, which means that our original function is equal to 1 over x minus 5 as long as x is not equal to 0, because that's the factor that we divided off. We'll bring that up to our limit so that we can use this twin function to evaluate our limit when x is approaching 0. Doing direct substitution where we replace the x's with zeros, we see this limit is equal to negative 1/5. So sometimes the limit laws don't apply, but we can use algebra to reconfigure the function and find that twin function that we're able to use to evaluate the limit.